Organic chemistry reactions HL1. Reactions of alkenes, electrophilic addition and mechanism. There's some special terminology to know first for organic reactions. First of all, we have nucleophiles, which means nucleus liking. These are electron-rich species that donate a lone electron pair to form a new covalent bond in a reaction. They attack areas of electron deficiency, or in other words, positive charges or dipoles. Some examples would be the hydroxide ion, the chloride ion, ammonia, and the cyanide ion. You notice all of these have lone pairs, and some of them are negatively charged. Electrophiles, or electron liking. Electron deficient species that accepts a lone electron pair from another reactant to form a new covalent bond in a reaction. They attack areas with high electron density, for example, pi bonds. Some examples of electrophiles: we've got bromine trifluoride, copper ion, we've got this positive bromine ion, which we'll get to later, and NO2+. We use curly arrows to show the movement of electrons in reaction mechanisms. The double-headed arrows, which you can see here, show the movement of an electron pair, and they will go from nucleophiles to electrophiles, obviously. The arrow tail, this bit here, is where the electron pair comes from, and the head shows where the electron pair is going to. Single-headed arrows, or fish hooks as we call them, show the movement of a single electron and used for homolytic fissions and free radical reactions. Okay, we also have both symmetrical and asymmetrical alkenes, and they undergo similar reactions, but the asymmetrical reactions can be a little bit more complicated. Symmetrical alkenes, no surprising, are symmetrical. They've got the same number of carbon atoms on each side of the carbon-carbon double bond. See but2-ene here. You could have a mirror there and it would look the same. Similarly with hex3-ene here, you have the same number of carbons either side. With asymmetrical or unsymmetrical, you just have a different number of carbons on either side of the double bond. So, addition reactions. Addition reactions are very straightforward. It is where you have a molecule just adding to another molecule. You can see you have two here, and the X and Y molecule is just adding on to the ethene. The double carbon-carbon bond structure in alkenes has our sp2 hybridized. Okay. The double bond is one sigma bond along the plane and one pi bond, which is above and below that plane. The pi bond electrons are above and below the plane of the nuclei and are less tightly held. Therefore, they have weaker bonds and break more easily. This pi bond is an area of electron density, and therefore it attracts electrophiles, or it is attracted by electrophiles. The general mechanism for electrophilic addition, there's a two-step mechanism, and we're not going to show the hydrogen atoms here. First step, you've got the let's say X and Y here, and the more positive atom will add to the double bond first of all, leaving a positive complex here and a negative ion over here. Step 2, the remaining negative ion then adds to the positive complex. If we want to add these two steps together, we can cancel out what's the same, and you get your overall reaction. Let's look at this example, an alkene with a hydrogen halide. Two-step mechanism overview. First step, the hydrogen bromide, it cleaves and the hydrogen forms the positive complex. It adds to the ethene, leaving a bromide ion. Then the second step, the bromide ion will add to this positive complex to form bromoethane. If we want to look at the overall reaction, cancel out these molecules and ions to get the overall reaction. So hydrogen halides as electrophiles. Something's going on here. Obviously the bromine is more electronegative, and so there's a negative dipole upon it. The bromine is more electronegative than the hydrogen. So electrons are shifting towards the bromine and away from the hydrogen. It forms a positive dipole on this hydrogen that is attracted to the regions of high electron density. In this case, the high electron density is the pi bond in the ethene. What about this reaction? We've got the hydrogen halide. We're going to look at the steps here in a bit more detail to find out what exactly is going on. The first step is a slow step. And we've got ethene here, we've got the double bond, and we've got the dipoles on the hydrogen bromide because of the electrophilic bromine. So the electrons are moving towards the bromine, meaning we've got this positive dipole here, we've got a negative center on the pi bond of the double bond, and these electrons move over towards the hydrogen. This causes heterolytic fission in hydrogen bromide, forming positive hydrogen and a negative bromide. The hydrogen attacks the pi bond, breaking it to form a carbon hydrogen bond. So we get this unstable complex, the carbocation forming, and bromide ion. Then we have the fast step. Oh no, sorry, 1 minute. There we go. We've got this positive center here, and so the double bond, let's say the lone pair of the bromide ion moves towards this, and a new bond is formed. So the unstable carbocation quickly reacts with the bromide ion, forming bromoethane. Final addition product is a saturated halogenated alkane. The conditions would be room temperature and protic solvents. A protic solvent is just a solvent that has hydrogens which are able to form hydrogen bonding. So water would be one, alcohols, molecules with NH2, etc. Another example, an alkene and halogen X2. So we've got 2 steps. First step, the bromine is cleaved to form this complex, positive complex, with 1 bromine going in there, and we'll get the bromide ion remaining. And secondly, the bromide ion is attracted to the positive complex to form the dibromoethane. If we want to look at the overall equation, we have to cancel out these ions to give us the direct addition. The halogens as electrophiles. Bromine is non-polar, as we know, but it becomes polarized as it approaches the electron-rich region of the carbon double bond. So as the bromine molecule comes towards the double bond, the pi bond, as it gets near the pi bond repels the electron cloud that's over here, pushing it over that away. And so you get a negative dipole and a positive dipole. The bromine atom nearest the alkene's double bond gains the delta plus, obviously. Okay, and therefore it then acts as the electrophile. Okay, Br plus. The first step, if we're going to do it more slowly, we've got this bromine molecule, and the dipoles form because the double bond here, the pi bond of the double bond, pushes the electrons from this bromine over here, giving the negative dipole and positive dipole. There's heterolytic fission in the bromine, making this electrophile and a nucleophile. The positive bromide attacks the pi bond, breaking it to form a carbon-bromine bond, giving us this carbocation, which again is unstable and it wants to react quickly, and the bromide ion. So this is the slow step, and then we have the fast step. We've got the unstable complex with the bromides present. The lone pair is attracted to the positive center, forming a bond, and we get the dibrom. What do you think? It's a saturated dihalogenated alkane. In conditions, room temperature, and again we'll have protic solvents. Third example, we've got alkene and interhalogen. Interhalogens are halogens which have two different halogens. So this time, what we've got ethene reacting with this molecule here. The chlorine is more electronegative than the bromine, so the electron cloud is going to push towards here, making a negative dipole and a positive dipole. The pi bond of the double bond will be attracted to the positive center here, and a bond will form, making the unstable complex and chloride ions. The fast step, the lone pair here will be attracted to the positive center, and the bond will form. Let me just move this along a bit. Okay. The two-step mechanism overview. You've got the ethene reacting with the interhalogen, forming positive complex and a chloride ion. Whichever is more electronegative will form the ion. The more electropositive one will form the complex. And then you get the fast reaction between the chloride ion and the complex. The overall reaction, you can just cancel them out like we did before. So like I've described, in this case, chlorine is more electronegative than bromine, so electrons are shifting towards the chlorine and away from the bromine, forming a positive dipole on the bromine that's attracted to the region of high electron density, which in this case is the pi bond in the double bond of the ethene. Okay, we're going to look at Markovnikov's rule. In the addition reactions of asymmetrical alkenes, you can get two organic products, but only one is favoured. For example, but-1-ene is asymmetrical. There's more carbons over here than there is over here. If that was to react with hydrogen bromide, you can get two possible products. 2-bromobutane is the major product, and we're going to talk about why this is. The halogen bonds to the most stable carbocation. The high concentration of positive charge on the carbon atoms make them unstable. Okay. the alkyl groups bonded to the carbocations have a positive inductive effect. And a positive inductive effect is just an electron donating effect. So the alkyl groups push electrons towards the carbocation, thereby reducing the density of the positive charge on the carbocation, making it more stable. Only one positive inductive effect is possible on primary carbocations. You've only got one methyl group here pushing electrons to stabilize the positive charge. So this is least stable. In secondary carbocations, you've got two groups with a positive inductive effect stabilizing this positive carbocation. So this is slightly more stable than this one. And the tertiary carbocations are the most stable because you've got three positive inductive effects stabilizing this positive center. So let's have a look. Option 1, reasons for the rule of carbocation stability. We're attacking the electrophile bond to carbon 2, producing a primary carbocation. So here you've got the alkene, the electrons of the pi bond being attracted to the positive dipole on the hydrogen because the electronegative bromine has become a negative dipole. This forms a primary carbocation here, and then we only have one group stabilizing it. And then we get the bromine here would be, it would be 1 bromo propane. Option 2, attacking electrophile bonds to carbon 1, producing a secondary carbocation. Again, we have the pi bond attracted to the positive dipole on the hydrogen because the bromine has a negative dipole because it's more electronegative. This time we have the hydrogen bonding to the carbon 1, and we've got a secondary carbocation. You can see here we have two methyl groups. It can stabilize that positive carbocation, and in this case that would get a bromine on the second carbon. So secondary carbocations are more stable than primary carbocations. Option 2 is favoured. The electrophilic atom, hydrogen here, bonds to the carbon with the most hydrogen atoms. Okay, let's see if you can predict the major product for these asymmetric addition reactions. You can press pause, have a think, and see what you get. Okay, if you've got 2 chloropropane and 2 iodo, 2 methylbutane, you would be correct. So let's have a look at additions with interhalogens in asymmetrical alkenes. Markovnikov's rule expressed in a more general term would be when an unsymmetrical reagent adds to an unsymmetrical alkene, the electrophilic portion of the reagent adds to the carbon bonded to the greatest number of hydrogen atoms. Okay, it's a bit of a mouthful. Here, if you can think about the intermediate step which will have occurred, we know that we either had a carbon plus here or we had a carbon plus here in the intermediate step. The carbon plus, if it was here, only had one group stabilizing it. If the positive charge was here, it had 2 areas stabilizing it. And so would want this would be the positive one. And the positive one always goes with the more electronegative atom. So the preferred product, 1 bromo, 2 chlorobutane. The mechanism produces the more stable secondary carbocation. Okay, see if you can predict the product for these asymmetric addition reactions. press pause and have a good think about it. That's right, 1 bromo, 2 chloropropane. We've got the chloro, the more electronegative species, in the middle. So it's got more things stabilizing the carbocation when it formed. And 2 bromo, 3 iodo, 2 methyl butane. Again, we've got the bromo having the 2 methyl stabilizing it. So the more electronegative bromine would go here, whereas the more electropositive iodine would have ended up here. Very good. And that's the end of that splendid